Hello, in this lesson we will have a look at internal classes and reflection. Let's start with internal classes. Java allows declaring a class inside another one, as you see here. External, it's just a normal class, and then inside we can declare an internal class. You see here that there are two different types of internal classes, one that are static and the others are not. In either case, you can declare also access control. For example, you can declare this internal class to be private. This has package visibility, but you can also declare public and protected internal classes. Let's start with static internal classes. Basically, static internal classes, they are declared inside another one, and this outer class here serves as a namespace. For example, here we have a class film, which has a title, has a director, and the director is declared as an internal class. Why would we like to do this? Well, maybe this class is auxiliary and we don't want to put this class outside. In any case, we declare that this class is public, which means that it can be used outside class film. For example, in this main here, I can access director, but I should use director in this way. The fully qualified name would be film, which is the outer class, and then director, which is the inner class. And the type, I can use again the fully qualified name. In addition, this internal class here can access all members of the outer class, even private ones. For example, if I would have a method here where I would have a reference to film, I would be able to access the field's title and director. Non-static internal classes are special because every object of that internal class should live inside an object of the external class. And just like static internal classes, they can access members of the external class even if they are private. So for example, this is the way you declare an internal class, non-static. Basically, you declare the access control and then again a normal class definition. And if you want to use the internal class from outside, you can because it's public. You have to, whenever you declare a new object of this internal class, you need to pass as a context an object of the external class. So you see that the new operator has this special syntax where I use an object of type external and then I create a new internal object. So if you think about this, this is the way you would actually the canonical way to implement composition, right? Because the part object lives inside a component object. Right, this is an example of the use of an internal class where we define a normal class author which has a name and a list of books that he or she has written, and then the class book is defined as an internal class. This class has an attribute title and a constructor. So we can create objects of type author using this constructor here, and then we can add books using this method. We just call the constructor of book and we delegate the addition of this new book to the collection to the constructor. The constructor of book basically assigns the title and, as you see here, adds the object to the books collection. You see that we can use this syntax here because books is not in this object here, but is in the container object, the author that contains the book. So we can refer to the variable this of the container object using author.this. Actually, in this case, this syntax would be equivalent to books.addThis because there is no ambiguity. This is an example of a main method where we create a new author, then we add two books, and because the internal class was declared as public, we can access that class from outside. For example, we can create a new book, but because it's a non-static internal class, we should always use a context object. In this case, it's object P, and because the class book is declared inside author, then we need to use the fully qualified name, which is author.book. And then using this syntax, we can create a new book inside object P. And remember, in the constructor of book, we were adding this book to the collection of books of the given author. Well, the same idea is applicable to interfaces, but nested interfaces are static by default. And actually, you have already seen an example of this when you have used the interface map. Remember that inside map, there is an interface called entry that is used to represent tuples, pairs of key and values. And they are useful whenever you use the method entrySet, because you can iterate through all these key value pairs. So in summary, you can use internal classes or nested classes as a way to group related classes, increasing encapsulation, and most probably you will use nested classes whenever you have an auxiliary class that you don't really want to expose externally, but is only used locally inside another class. There are other options. So for example, you can declare classes inside methods. These are called anonymous classes. And they are called anonymous because they don't have a name. So you use basically a base class or base interface to create a subtype of it and instantiate such a new class on the spot. What can you do with those objects that you create on the spot? Well, you can declare methods inside that can access members of the external class and can use local variables in a constant way, so you cannot change those variables inside the anonymous class. Why would you like to use an anonymous class? Well, it's very handy, for example, when you build graphical user interfaces using Swing, for example. Recall that in Swing you can create frames, then you can create widgets and like buttons or text fields, and then you need to add behavior to those components using listeners. What is a listener? A listener is an object that conforms to an interface, that implements an interface. Sometimes the code that goes into these listeners is just very small, and it would be quite cumbersome to create a class that implements the interface and then add all the methods inside and so on. So here anonymous classes, they came in very handy. And this is an example where I take action listener, which is an interface, and you see I use new, the name of this interface, and I'm using the name of the interface as if it would be a constructor. Instead of in anonymous classes, you can use any constructor of any class, and then using these brackets here, you can add new methods or override existing methods. For example, here we are overriding action perform, right? And then we are basically adding this line of code here that, as you can see, we can access field, and field is a variable. Here is declared as final, but it doesn't need to be final. Even if it is not final, I can access the variable here, but I would not be able to change it. And this way, anonymous classes are a way to avoid creating explicitly new classes that are only going to be used once in this place here. It's also very interesting that this idea of anonymous classes can be used in combination with enumerations. Remember, enumerations are objects. And using this syntax for anonymous classes, where I open the curly brackets here, we can, for example, declare abstract methods inside an enumeration. For example, this is an enumeration for logical gates that have an AND and an OR, and then I have a method calculate that takes two booleans and returns a boolean. It's an abstract method, so we should override this method inside any concrete subclass of logical gate. Well, we don't have subclasses in enums, right? But we do have we do have objects for the enumeration literals like and or. Therefore, using the anonymous class syntax, we can override here this method, right? And then we can provide code for the AND calculation and for the OR calculation. So that's also a very typical way to provide behavior to enumerations. You can declare methods here outside the enumeration literals and then override those methods using the anonymous class syntax. Right, finally, we are going to have a look at reflection. What is reflection? Reflection means that I can do computations inspecting the behavior of or the structure of a program while it is running. So it's very powerful because it allows you to do many fancy things, for example, from simple things like inspecting the type of an object at runtime, or to list what are the attributes of a given object without knowing the type, or create objects when we have the type of the object in a string. So for example, we can ask from the console what is the type of the type that you want to instantiate, and then the user types in a class name, and then we can instantiate an object using that string, or we can even access private attributes or methods using reflection. But reflection should be used with caution because it's less performant and it has security restrictions, so you cannot execute reflection code within applets, and you can do things that may be incorrect or give rise to error, like exposing internal members, like private members. Right, let's have a look at the simple type of reflection, which is given by the instance of operator. The instance of operator is a binary infix operator that takes two parameters, a reference and then a type. This type can be a class, can be an interface, can be an enumeration. And basically, this instance of returns true or false. Returns if the object type at runtime is compatible with the type that is given as a second parameter. It's okay to use it, but sometimes, quite frequently, it actually signals a bad code design, as we will see next. But first, we will see an example of how to use instance of. So we have a class A, then I have a subclass B that extends A, and then we have another class, reflection. Then we create an object A whose type is B, but the declared type is A. That's fine because B extends A, so this is compatible. We don't need a casting here, as you all know. And then we are asking here whether A is an instance of B. That's how the instance of operator is used. And the idea is that here the operator will tell me if A is compatible with B at runtime. And if it is, then we print type B, otherwise we print type A. In the output, it prints type B because it's compatible at runtime. A is an instance of B. Well, you can use this, for example, before castings to avoid casting errors, to make sure that actually if I want to cast A to type B, we want to make sure that actually it's an instance of B. Right, but as we said before, sometimes the use of instance of signals an error in your design. Let's see a typical example that happens many times, so please look at your code, and if you have this pattern here, please fix it because it's a design error. So here we have an abstract class whose name is booking, which has a code and then has a getter. And then we may have other bookings that extend booking, or flight bookings that extend booking, or other types of bookings like travel bookings and so on. Then we have a different class, booking manager, that has a collection of bookings and then has a method cancel to cancel the booking. The idea here is that given a code, we have a method getBooking that returns the booking that has that code, right? Nothing very spectacular, but look at what we do here. Now we check whether R is an instance of hotel booking, flight booking, travel booking, because in every case we need to cancel using different code. So for example, a hotel booking, we need to connect to a given API, and a flight booking, we need to connect to another one, and so on. So here we put specific code depending on the real type that R has. Well, if you look at this, this is so extremely ugly and not extensible that probably is hurting your eyes. So a much better design is given here. So the idea here is that because we can cancel depending on the subtype of booking, it's much better to say, okay, any booking can be cancelled. So let's put a name to this code that was here before. Let's call it cancel. And then let's put the code where it belongs. So we put here the code to cancel a hotel booking, and we put here the code to cancel a flight booking. And you see that these cancel methods here are overriding this method. That's a much better design and simplifies a lot the cancel method here, because we basically get the booking, we just check if it is null, and otherwise we just call cancel, and then each class knows how to cancel itself. This is a much better design for many reasons. One of them is extensibility, right? If I want to add a new kind of booking, then I just add the new class here, and then I need to fill in the cancel method. Yeah? Each booking needs to cancel, knows how to cancel itself. So this code is here, is encapsulated in this class, and is not around any other classes. So if I would have the other design, I would need to go into all other code, all the rest of the program, to look where I need to change in response to adding this new class. So this is a much better design. So please don't do the other design ever. Right. So reflection involves a representation at runtime of the structure of your code, and this structure you can query, and sometimes you can modify. So Java gives you a class whose name is class that represents the structure of a class, an interface, or an enumeration, basically a type. Class does not have a constructor, but you need to create those objects using typically getClass. So here you have an object of type string, you call getClass, and then you obtain an object class with the internal representation of the strings. For example, one thing you can do is obtain, obtaining the name or the simple name. In this case, that's the fully qualified name. And then once you have the class, then you can say, for example, what attributes do you have, what fields do you have, and then you can even change the value of the fields or invoke the methods using those reflective methods. We will see an example here of the power that reflection gives you. Here we have a class, a normal class with a private attribute name, an empty constructor, and then a one parameter constructor. I'm declaring this 0 parameter constructor on purpose because reflectively we will create objects of type course. And then we have just a toString. Then you see here that we have a main method where I obtain a class object in a different way. I use forName. For name here, I give the name of class, which is course, this one here, and then I obtain the class object, right? What can we do with it? For example, I can say, I can invoke a new instance to create an object of the class. But new instance here needs to use a 0 parameter constructor, that's why I added it here, right? So now I have as ASIG, which is an object of type course. I have assigned it to object because that's what new instance returns. Now what I can do is I can get a field, right? Field is a reflective class again. It's a class that is used to represent what fields, what attributes a class has. So I can get the field name and I can change the accessibility, so the access control. So it was private, but now I say, okay, this is going to be public. This is going to be public when I access it through reflection. If I access it normally, then it's still private. But setting set accessible to true allows me to change the value of the field with set. So remember, FLD is the field object, and then I can say, okay, change this attribute of ASIG, which is the object, and set it to ABS. And then if you run this program, you will see that I was able to change the value of a private attribute by using reflection. But again, use reflection only when it is really needed, because it's much less performant and you can do strange things that can break your program.